just so that we make sure that we're getting this trig function thing down well. So let's construct ourselves some right triangles. Let's construct ourselves some right triangles. And I want to be very clear, the way I've defined it so far, this will only work in right triangles. So if you're trying to find the trig functions of angles that aren't part of right triangles, we're going to see that we're going to have to construct right triangles. But let's just focus on the right triangles for now. So let's say that I have a triangle where, let's say this length down here is 7, and let's say the length of this side up here, let's say that that is 4. And let's figure out what the hypotenuse over here is going to be. So we know, let's call the hypotenuse h. We know that h squared is going to be equal to 7 squared plus 4 squared. We know that from the Pythagorean theorem, that the hypotenuse squared is equal to the square of each of the sum of the squares of the other two sides. H squared is equal to 7 squared plus 4 squared. So this is equal to 49 plus 16. 49 plus 16. Let's see, 49 plus 10 is 59. Plus 6 is 65. It is 65. So this h squared, we write h squared. That's a different shade of yellow. So we have h squared is equal to 65. Did I do that right? 49 plus 10 is 59, plus another 6 is 65. Or we could say that h is equal to, if we take the square root of both sides, square root of 65. And we really can't simplify this at all. This is 13. This is the same thing as 13 times 5. Both of those are not perfect squares, and they're both prime, so you can't simplify this anymore. So this is equal to the square root of 65. Now let's find the trig. Let's find the trig functions for this angle up here. Let's call that angle up there theta. So whenever you do it, you always want to write down, at least for me it works out to write down, SOHCAHTOA. SOHCAHTOA. I have these vague memories of my trigonometry teacher. Maybe I read it in some book, I don't know, about some type of Indian princess named SOHCAHTOA or whatever. But it's a very useful mnemonic. So we can apply SOHCAHTOA. Let's say we wanted to find the cosine. We want to find the cosine of our angle. We want to find the cosine of our angle. You say SOHCAHTOA. So the ka tells us what to do with cosine. The ka part tells us that cosine is adjacent over hypotenuse. Cosine is equal to adjacent over hypotenuse. So let's look over here to theta. What side is adjacent? Well, we know that the hypotenuse is this side over here. So it can't be that side. The only other side that's kind of adjacent to it, that isn't the hypotenuse, is this 4. So the adjacent side over here, that side it's literally right next to the angle. It's one of the sides that kind of forms the angle. It's 4 over the hypotenuse. The hypotenuse, we already know, is square root of 65. So it's 4 over the square root of 65. And sometimes people will want you to rationalize the denominator, which means they don't like to have an irrational number in the denominator, like the square root of 65. And if you want to rewrite this without a irrational number in the denominator, you can multiply the numerator and the denominator by square root of 65. This clearly will not change the number because we're multiplying it by something over itself, so we're multiplying the number by 1. That won't change the number, but at least it gets rid of the irrational number in the denominator. So the numerator becomes 4 times the square root of 65, and the denominator, square root of 65 times square root of 65, is just going to be 65. We didn't get rid of the irrational number. It's still there, but it's now in the numerator. Now let's do the other trig functions, or at least the other core trig functions. We'll learn in the future that there's actually a ton of them, but they're all derived from these. So let's think about what the sine of theta is. Once again, go to SOHCAHTOA. The SO tells us what to do with sine. Sine is opposite over hypotenuse. Sine is equal to opposite over hypotenuse. Sine is opposite over hypotenuse. So for this angle, what side is opposite? Well, you just go opposite it, what it opens into. It's opposite the 7. So the opposite side is the 7. This is right here, that is the opposite side. And then the hypotenuse, it's opposite over hypotenuse. The hypotenuse is the square root of 65. Square root of 65. And once again, if we wanted to rationalize this, we could multiply it times the square root of 65 over the square root of 65. And the numerator we'll get 7 square roots of 65, and in the denominator we will get just 65 again. Now let's do tangent. Let us do tangent. So if I asked you the tangent of theta, once again, go back to SOHCAHTOA. The TOA part tells us what to do with tangent. It tells us that tangent is equal to opposite over adjacent, is equal to opposite over adjacent. So for this angle, what is opposite? We've already figured it out. It's 7. It opens into the 7. It's opposite the 7. So it's 7 over, what side is adjacent? Well, this 4 is adjacent. This 4 is adjacent. So the adjacent side is 4. So it's 7 over 4. And we're done. We figured out all of the trig ratios for theta. Let's do another one. I'll make it a little bit concrete, because right now we've been saying, oh, what's tangent of x, what's tangent of theta? Let's make it a little bit more concrete. Let's say, let me draw another right triangle. There's another right triangle here. Everything we're dealing with, these are going to be right triangles. Let's say the hypotenuse has length 4. Let's say that this side over here has length 2, and let's say that this length over here is going to be 2 times the square root of 3. We can verify that this works. If you have this side squared, so you have, let me write it down, 2 times the square root of 3 squared plus 2 squared is equal to what? This is 2, this is going to be 4 times 3 plus 4. And this is going to be equal to 12 plus 4 is equal to 16. And 16 is indeed 4 squared. So this does equal 4 squared. It does equal 4 squared. It satisfies the Pythagorean theorem. And if you remember some of your work from 30, 60, 90 triangles that you might have learned in geometry, you might recognize that this is a 30, 60, 90 triangle. This right here is our right angle. I should have drawn it from the get-go to show that this is a right triangle. This angle right over here is our 30-degree angle, and then this angle up here is a 60-degree angle. And it's a 30, 60, 90 because the side opposite the 30 degrees is half the hypotenuse, and then the side opposite the 60 degrees is a square root of 3 times the other side that's not the hypotenuse. So with that said, this isn't supposed to be a review of 30, 60, 90 triangles, although I just did it. Let's actually find the trig ratios for the different angles. So if I were to ask you, or if anyone were to ask you, what is the sine of 30 degrees? And remember, the 30 degrees is one of the angles in this triangle, but it would apply whenever you have a 30-degree angle and you're dealing with a right triangle. We'll have broader definitions in the future. But if you say sine of 30 degrees, hey, this angle right over here is 30 degrees, so I can use this right triangle. And we just have to remember SOHCAHTOA. Let me rewrite it. SOHCAHTOA. Sine tells us, tells us what to do with sine. Sine is opposite over hypotenuse. Sine of 30 degrees is the opposite side. That is the opposite side, which is 2 over the hypotenuse. The hypotenuse here is 4. It is 2/4, which is the same thing as 1/2. Sine of 30 degrees, you'll see, is always going to be equal to 1/2. Now, what is the cosine? What is the cosine of 30 degrees? Once again, go back to SOHCAHTOA. The ka tells us what to do with cosine. Cosine is adjacent over hypotenuse. So if we're looking at the 30-degree angle, it's the adjacent. This right over here is adjacent. It's right next to it. It's not the hypotenuse. It's the adjacent over the hypotenuse. So it's 2 square roots of 3 adjacent over the hypotenuse, over 4. Or if we simplify that, we divide the numerator and the denominator by 2. It's the square root of 3 over 2. Finally, let's do the tangent. The tangent of 30 degrees. We go back to SOHCAHTOA. SOHCAHTOA. TOA tells us what to do with tangent. It's opposite over adjacent. We go to the 30-degree angle, because that's what we care about. Tangent of 30. Tangent of 30. Opposite is 2. Opposite is 2, and the adjacent is 2 square roots of 3. It's right next to it. It's adjacent to it. Adjacent means next to. So 2 square roots of 3. So this is equal to, the 2's cancel out, 1 over the square root of 3. Or we can multiply the numerator and the denominator by the square root of 3. So we have square root of 3 over square root of 3. And so this is going to be equal to, the numerator is square root of 3, and then the denominator right over here is just going to be 3. So that's, we've rationalized it, square root of 3 over 3. Fair enough. Now let's use the same triangle to figure out the trig ratios for the 60 degrees, since we've already drawn it. So what is the sine of 60 degrees? I think you're hopefully getting the hang of it now. Sine is opposite over adjacent. So, from the SOHCAHTOA, for the 60-degree angle, what side is opposite? Well, it opens out into the 2 square roots of 3. So the opposite side is 2 square roots of 3. And for the 60-degree angle, it's opposite over hypotenuse. Don't want to confuse you. So it's opposite over hypotenuse. So it's 2 square roots of 3 over 4. 4 is the hypotenuse. So it is equal to, this simplifies to square root of 3 over 2. What is the cosine of 60 degrees? Cosine of 60 degrees. So remember, SOHCAHTOA, cosine is adjacent over hypotenuse. Adjacent is the 2 side. It's right next to the 60-degree angle. So it's 2 over the hypotenuse, which is 4. So this is equal to 1/2. And then finally, what is the tangent? What is the tangent of 60 degrees? Well, tangent, SOHCAHTOA, tangent is opposite over adjacent. Opposite the 60 degrees is 2 square roots of 3. 2 square roots of 3. And adjacent to that is 2. Adjacent to 60 degrees is 2. So it's opposite over adjacent, 2 square roots of 3 over 2, which is just equal to the square root of 3. And I just want to, look how these are related. The sine of 30 degrees is the same thing as the cosine of 60 degrees. The cosine of 30 degrees is the same thing as the sine of 60 degrees. And then these guys are the inverse of each other. And I think if you think of a little bit about this triangle, it'll start to make sense why. We'll keep extending this and give you a lot more practice in the next few videos.